I'll be presenting GHunter or GHunter. My name is Eric, and this was joint work with my colleagues at KDH in Sweden. So I'll dive straight in and do a little background. So inheritance in JavaScript. The way inheritance works is fundamentally prototype-based, and the way you can think about this is that existing objects are reused for the purpose of inheritance. So the example on the screen, you have object A. It has this property that we call dunder proto, and it has a reference to another object, in this case, the root object prototype. And this way it gets access to functionality such as converting itself into a string. And similarly, object B has a dunder proto reference that references object A, and transitively that way inherits from the root object prototype. The problem, however, is that there is no stratification. And you can think of stratification as the idea that there should be a separation between this reflective nature of the language, such as accessing your parent class, and regular programming constructs. And in JavaScript, this is not the case. Dunder proto is just a regular string that anyone can access. And to illustrate the problem with this, I have this example web server that just allows users to store some key value pairs on the server in memory. So for a regular user, what will happen is it states its user ID, and the user will be found in the lookup table in the object, and it will store the key and the value pair that the user specified in its object. Now, when there is a malicious user comes along and says, hey, you know what? My user ID is not a number, it's actually dunder proto. The server will happily comply with this. It knows an object at the point dunder proto, and so it will just add the key and the value that the attacker specifies to the root object prototype, thus allowing all objects in the runtime to inherit this key value pair. And so this is what we call prototype pollution. So the lack of stratification leads to pollution. Now, in the title of this presentation, we're talking about gadgets, not a pollution. So what is a gadget? A gadget is a piece of code that's otherwise benign, but inadvertently reads from such a polluted property and then performs some security-sensitive operation. So to illustrate this as well, I will continue with the same server from before, but now I will put my focus on line 3, this exec command, which will just run a command. So note here that the input is just a fixed string. Like this looks fine. There's no user input or anything to worry about. But if you look at a hypothetical implementation of this API, we see that it takes the command string that we saw and then an options object as well. In this case, we didn't provide an options object, so what the function will do is it will instantiate some default object as a fallback. Then the next thing that will happen is it will try to determine the shell in which we want to execute this command. And for this, it will ask the options object, hey, do you have a shell property? And we just created the options object. It's empty, so it doesn't have it. But remember what the attacker did. It actually polluted the shell property, and thus it will actually find it and store it in the local variable. The local variable will then be used on the next line to actually run the command we want to run. And what this will look like is that the attacker-controlled value, calc in this case, will be spawned, and as a result, will have remote command execution. Now, in the title, again, we said universal gadgets, so what are those? Universal gadgets are gadgets that are present in the JavaScript runtime themselves, so they affect nearly all programs that run on top of these runtimes. And our fundamental research question in this work is, can we find such universal gadgets automatically and efficiently? The thread model for our work is as follows. We consider server-side JavaScript and TypeScript applications running on top of either Node.js or Dino, which are two of the most popular server-side JavaScript engines. We assume the application is vulnerable to pollution, which prior work has shown, and there's also lots of known vulnerabilities out there that for pollution in packages. And again, our goal is to find gadgets across a wide variety of use cases, such as arbitrary code execution or server-side request forgery. And just to reiterate, what we're trying to do here is we're trying to find undefined property reads, such as shell in this example, and we want to know whether it flows into security-sensitive APIs, such as op spawn in this example. So how do we do this? Well, we built GHunter, which is a tool for semi-automatically finding these gadgets. Fundamentally, our approach is driven by the pre-existing test suites of the runtimes, And to give you a little bit an idea of scale here, the Node.js test suite is almost 4,000 tests big, and the Dino test suite is about 5,500 tests big. And for both runtimes, we achieve over 90% function coverage, meaning that most of the APIs in these runtimes are covered by our approach. What we'll do first is we will just run the test, basically, and the goal here is to find these undefined property reads that we saw earlier. The way we do this is we modified the V8 JavaScript engine. This spans about 8 files and 200 lines, and the goal here is to be able to detect whenever a missing property read occurs and then store that somewhere so we can refer to it later. Note that V8 is shared by both Node.js and Dino, so this was one operation that was useful for both runtimes. And essentially what we do is we just run each test and look and capture all the undefined property accesses. So on the slide, we have the exec function from before, hypothetical implementation, and we have some hypothetical test suite with 2 tests that run the exec function. And what will happen is by running these 2 tests, we will detect, let's say, 4 properties. So we already know that we will detect a shell property. We've run through this example before, but let's say we also find these 3 additional properties. Maybe they occur in the sanitize API. What we do next is we run the test suites again, but this time we use these undefined properties that we detected as an input to the test run. And our goal is to find these source to sink flows that I mentioned before. So what do we consider as sinks? It's essentially we consider all flows into native code as sinks, and this includes binding code, which are extensions provided by Dino and Node.js to interact with the system, as well as dynamic code evaluation APIs, such as the eval function in Node.js. And what we do now is we don't run each test once, we actually run it n times, once for each property that we detected. So in this example, we'll first run the test, and we will pollute the all property with a fixed value. With the all property, we won't find anything, so we move on to the next property, flags. Same story, we won't find anything. But when we get to shell, we already know what's going to happen, right? We pollute the property. We know that the implementation will start reading this shell property, at least in the first test case, because we don't provide an options object. This will flow into the local variable. In turn, this will flow into the template literal, which will be called in the ops sink. And so the way we detect this flow at the sink is we basically just inspect all the arguments for the magic value that we polluted the property with. And this is a form of very lightweight taint tracking that has proven very effective for our purposes. And to complete the cycle, we need to run the test with the last property polluted as well. Then we do another test run, and again, we use the source properties as input, but in this case, we're interested in unexpected terminations such as seg faults. The idea here is very similar, but a crucial point to make is that we do this on a completely unmodified engine to make sure it's not our changes that cause the seg fault or the other unexpected termination reason. I won't walk through this again because it's conceptually the same story as before. In the end, we take the 2 results from the previous 2 steps, so the source to sink flow and the unexpected termination, and we want to generate candidate gadgets in a serif format. On the slide, you can see a preview of what this looks like. So we do some pre-processing as well to filter out duplicates, etc. And then we manually review all these results and construct proof of concept gadgets where possible. As a result, we found 56 such gadgets in Node.js and 67 in Dino across a wide variety of attack classes. And to illustrate, I will give 2 examples. So first, an arbitrary code execution gadget in Node.js, where if you try to import a relative file and you pollute the property called source with some JavaScript script, what will actually happen is that the file isn't imported, the script is just executed. For Dino, a server-side request forgery gadget that allows you to control the fetch API. So on the slide, we just try to fetch some information from some website. But if we pollute these 4 properties to control the URL, the method, the body, and any headers, what we find is that we completely change the request to a completely different request, essentially. So in conclusion, we have presented a semi-automated pipeline for finding universal gadgets in JavaScript runtimes, which is available at the link or the left QR code. We used GHunter in a study of universal gadgets in 2 runtimes, finding a total of 123 exploitable gadgets. We collect these in a separate repository where we also have other known gadgets as well. You can find this at the other URL or the QR code on the right. And we have more in the paper. For example, we have a comparison to a paper called Silent Spring, which kind of introduced the idea of universal gadgets in JavaScript runtimes. We also systematize existing mitigations for gadgets and prototype pollution. And we use this in a study of existing mitigations and find one new high-severity exploit in Kibana due to an incorrectly fixed gadget. That's it. Thank you very much.